la dottoressa Sara Moccia.
Good morning, everybody, and thank you, Professor Burattini, for introducing me. This work comes out from the collaboration between the VRI lab of our university and Vicomtech, which is a research center located in San Sebastián in Spain. And from this collaboration, I experienced more about computer vision and deep learning in surgery. Image-guided surgery is a common practice nowadays, and images play a fundamental role for real-time visualization for surgical navigation. So image fusion among different modalities and at different times for treatment is getting more and more attention to improve intraoperative image quality and also to provide more information at a time. In particular, the clinical context of the endovascular repair for abdominal aortic aneurysm is considered, as it is a minimally invasive treatment in which the images play a fundamental role as through them, thanks to them, is it possible to insert a catheter through the femoral artery that has to reach the latest section of the aorta, where a stent needs to be left in place to avoid its rupture. So the fluoroscopic guidance is essential, as well as the preoperative tomographic images are extremely important for the planning of the surgical settings. And in fact, they provide high quality information, high quality images, and also measurement information about, for example, the length and the size of the aneurysm. Hence, for this surgical context, a huge improvement can be obtained from a proper fusion of the preoperative images and intraoperative images can be, and it's fundamental for that we have a proper registration process, which means that the spatial correspondence between images taken at different time instant or from various point of view can be established with making a better visualization of the tools and more accurate information about the current position in relation with the planned trajectory. In relation with registration as traditional registration, it is generally approached with the same way, following like this flow. And to register moving image to a reference image, a metric based on distance needs to be optimized to find the optimal transformation parameters that are applied to the moving image. And the transformation is actually the mathematical operator that map one dataset into the other. So this process is done iteratively until is reached convergence in terms of metric reduction. There are many classifications associated with state-of-art registration methods. Some of them are related with the images and the type of data, like the dimensionality and the images modalities. Others are completely dependent on the method that has been chosen, like the choice of rigid or deformable transformation, or the nature of the registration basis, if it is extrinsic, and so based on fiducial point or markers, or intrinsic based, and it relies only on the anatomies of the images shown. In particular, for the 3D, 2D intramodality registration, like in the case of matching between CT images and fluoroscopic images, intensity-based methods can be applied, and in this case is needed to have dimensional correspondence, returning to voxel-wise matching or pixel-wise matching. The latter case is the most common, in which the projections of 3D images on a plane are created, and like the ones shown in the image, that are the one on the right, on the left, that are reconstructed images called digitally reconstructed radiographs, and these are comparable with the fluoroscopic images on the right. Despite the huge research in this field, however, there are still limitations, mainly associated with a small capture range, and so that leads to the tendency to converge to a wrong optimum, and so make a mixed registration. But also other issues are also the computational complexity and iterativity of the processes that also are time consuming, and so lead to insufficient frame rate. Therefore, this work aims to registration through the development of a convolutional neural network that automatically identify the transformation parameters to get image alignment, And the final purpose of that is to improve the endovascular navigation for the abdominal aortic aneurysm treatment through a proper registration of the lumbar spine, which are considered as reference structures. In particular, as shown in the workflow, the first part of this work has been dedicated to the development and the generation of the projection that needs to simulate the behavior of fluoroscopic images. And the second part is dedicated to the training of a convolutional neural network that takes these images as inputs and predicts their 3D orientation. The whole work has been conducted in Python environment, and Insight Toolkit has been used for the images analysis, and TensorFlow in Kira's library for the convolutional neural network training inside the Microsoft Azure cloud. The image dataset has been created using an open source dataset of CT scans called SpineWeb3. And at the same time, 25,000 transformations has been generated to be applied to the CT scans and simulate patient movements. The transformation are random, rigid, and constrained in specific ranges uniformly distributed. And these ranges are defined considering the fact that the images are projections on the coronal plane, and so with greater ranges variabilities for the out-of-plane parameters. The CT scans, once transformed, are projected and then cropped within a region of interest, which is defined around the coordinate center of a vertebra, which corresponds to the coordinates of the center of rotation of the applied transformation. The transformation are perspective transformations, and for the projections, even the intensity ranges has been modified to be comparable to the fluoroscopic ones. So this process led to the formation of 5 datasets of 25,000 coronal intensity-based projections, and it is evident that the anatomical characteristics of each vertebra are part of the difficulties of the identification of the pole by the neural network. This convolutional neural network is composed by 3 5x5 convolutional layers with interposed max pooling layers of strike 2, and all are processed by ReLU activation function. And after flattening, there are other 2 fully connected layers with ReLU activation neurons. And then from the output layer, the transformation parameters comes out. The dataset has been split into 20% for testing session, and of the remaining 60% for training, another 40% for validating the network. The data are fed into the network into batches of 10 for 80 epochs. Adam optimizer has been used, and the mean absolute error has been chosen as loss function. Then looking at the results, as common in regression analysis, plotting is the most natural way to see the overall trends of the results. So for each training data, the mean absolute error and the mean square error has been plotted to see how much the prediction are dependent on the data set, and also how the different morphology can affect the overall prediction. And we can see that more or less the convolutional neural network is stable and it has the same accuracy, so it has no problem of domain adaptation, which is the same and say that it generalizes well for different vertebral anatomy. Then to see with how much accuracy these parameters are predicted, the mean absolute errors for each test sessions are compared, and the convolutional neural network has to learn 3D orientation from projection images, so on the coronal plane. So I was expecting to have, as also confirmed from literature, that some of these parameters would have been more difficult to identify, and so we higher values of the errors, which are the ones out of the projection plans. So we can consider it as we have an incomplete identification of the parameters that affects the overall performance. In conclusion, we can say that even though all 6 transformation parameters in a row cannot be identified with sufficient accuracy, at least with the current settings, this could be a good starting point to explore this complex field and experiment other architecture, or considering separate convolutional neural network for each regressor. So to keep going with researches, we are going to submit to the International Workshop on Artificial Intelligence for Healthcare Applications. A way to obtain a good registration in an automatic, fast, and reliable way will have a silent but a huge impact in navigation surgery. So thank you for the attention.
Thank you very much. Are there any questions? Professor Chiaraluce?
Just a very short question about an issue that you mentioned in the last slides of the presentation, that is the complexity of these procedures. You mentioned the importance to proceed with the accurate evaluation. Are the current algorithms already useful in practice, let me say, in the sense that they can be managed with a reasonable complexity or not?
Actually, it's not enough, because the value or the accuracy of the errors is too high compared with what we really can use in surgery, which the values of the error would be very minimal, so lower than 0.05 should be the best. So it should be improved, but this could be at least, we know that we can go on with this in this way and try to differentiate, for example, different convolutional networks, to train them to just identify one parameters, and so make different type of trials. But this could be a way to have a real-time registration for real in surgical environment.
Thank you. And the choice of the convolutional neural network, you think is the optimal choice, or you can consider the possibility of alternatives?
Other alternatives can be evaluated. Actually, I was thinking about trying also DenseNet and VGG network, but in this case, I decided to try this way and to consider convolutional neural network, focusing on previous studies, in which, in particular, one study conducted by Miao in 2016. In that case, the registration was conducted into a little bit different ways, and the images were considering also the presence of a device. So the presence of a device makes it even easier to identify, let's say, the images and register the orientation, as it is a parametric object, so easier to identify. But the structure, the general structure was more or less the same. So I tried to follow a previous study which was quite accurate. So that was the reason why I chose the convolutional neural network.
Thank you very much.
To you.
May I ask a question?
Yeah, sure.
Thank you. Yes. If I understood well, these images are used by doctors or surgeons to, let's say, estimate or get an idea about the dimensions, for example, of the aneurysm they have to process. So my question is, did you try, or at least did you find in the literature, if together with the evaluation of the accuracy of your CNN approach, is it also important to evaluate the uncertainty improvement in terms of dimensional evaluations? I mean, these images have, let's say, an information which is related to the real dimension of the, let's say, physiological tissue which has to be treated. So my question is, does this method also improve the uncertainty in the evaluation, for example, of the length or size of the aneurysm which has to be treated by surgery?
Yeah, actually, the final purpose is to obtain a better registration, to improve the quality of the intraoperative image that generally has a lower resolution, and so more information also, like the information of the dimensional of the aorta, or of the size of of its length, can be overlapped to the representation of the intraoperative images. Or even rendering or of the abdominal section, for example, can be represented, overlapped with the real-time fluoroscopy image. So actually, this is like the contest which is possible to obtain an improvement of the surgical environment.
Okay, thank you so much.
Thank you.
Okay, thank you very much. The next candidate is Panbianco Benedetto.